Greetings from Munich. And so, yes, before I start, I want to thank a few people and highlight their contributions. I'm working together with Christoph Zaruli for quite a while now. He's in Strasbourg University, and a lot of the material that I present is from a collaboration with him. David Alata and Paula Köhlemeyer contributed with some codes, and also Nathan Simmons from Lawrence Livermore. You may know these people. And then there are a number of my PhD former master students who contributed a lot. Thomas Kust, he was a former PhD student of Peter Bunge here in Munich, who actually contributed with a mineral physics model, a thermodynamic model similar to what Lars Dixrud and his group does. And then also work together I did with Christ Nollet, Jeroen Ritzimer, and also Lars Dixrud, Gerd Steinle-Neumann, people who had all their share in what I present today. And I also want to highlight people from our supercomputing center, the Leibniz Rechenzentrum, and the visualization group, who did a great job in some of the visualizations you will see later on. Okay, so here the outline of what I want to present today. I want to motivate a little bit the importance of mantle circulation modeling, the importance of mantle dynamics. Many of this or much of this will be, I think, familiar to you. And then from there on, I want to actually motivate why I think it's really important to go in a quantitative way from the mantle circulation models and the predictions they make, and check them against seismic information in terms of the amplitude of the signal. I go into the details of that, and there, in doing so, there are a number of challenges that we face, and these are related to some sometimes quite severe nonlinearities, and this actually prohibits a simple scaling, and we will actually really see why we need full waveform simulations using SpecFEM. So I go here later on into some technical aspects of linking the mantle circulation models, MCMs, with the SpecFEM 3D globe simulations. And then from there on, I will show a few of the results of the last years and a little longer ago, looking at lower mantle structure and how lower mantle structure actually from the geodynamic models is seismically seen. We look into the standard deviation of body wave travel time residuals and how they relate to temperature anomalies in the models. I will actually then speak about dispersion of travel time residuals just in a purely elastic mantle, so due to focusing and defocusing effects. And this is the beauty of doing this in a virtual environment, that you can switch off attenuation. And so we get the pure signal from the elastic structure. And then later on, I will explore a little bit effects of uncertainties, in particular in the mineralogy, the anelasticity correction, and then come finally to some outlook also at the very end of where I think this is important to be brought all this research. Okay, the importance of mantle dynamics. What we do here in Munich is we do a lot of forward and inverse simulations of mantle flow. And it's important because the mantle provides the plate driving forces. So we really need to get a good understanding and a handle on the forces acting at the base of the plates, so that we can better think about and simulate and model plate tectonics. And also, I think a topic that is getting a lot of attention recently is that the mantle controls the core heat loss over geologic time, and therefore impacts the geodynamo and the reversal frequency pattern of the geodynamo over times of tens of millions of years and longer. So what you see here is this simple cartoon of what might happen in the mantle, and related to that, the plate tectonic motion will lead to seismicity. The beauty of that in some sense is that seismicity is the primary information that we get about deep earth structure, so we can use that actually to study that cause of the natural hazards that we see here. In order to understand mantle dynamics, there are a number of challenges that we still face today. And first of all, the buoyancy distribution in the mantle is not really known. There are limits to seismic tomography in really showing us the buoyancy distribution, because we don't get density directly from tomography, and any tomography always is a blurred and a low fidelity version of the true Earth structure. Therefore, as I will highlight later on, we think we can learn a lot from just doing forward modeling instead of doing the inverse approach that is quite common. And a second problem in understanding the dynamics of the mantle is that the material parameters, in particular the viscosity, is not well known. It's not really well constrained. And this means that we need to find ways to actually check models that we run with different material parameters, different rheologies against any observation that we have available, at best at all, against all observations together. So one question that I addressed over the course of the last 10, 15 years is, what is the origin of the heterogeneity in the lower mantle? And to illustrate that here, I show a number of tomographic models. These are a few older ones, but the point I want to make here doesn't depend on that. We see here a few depth slices from just below the lithosphere roughly to the core mantle boundary. And I want to focus directly on the lower mantle structure. What we see here is that on the broad scales, the models agree quite well. On the finer scales, they don't agree that well. But what is important to note here is that the amplitude of the signal, so the color saturation here on the color bar between -2 and 2% in shear wave velocity is such that the amplitudes are smaller in the mid-mantle, and they all increase in the amplitude of the signal towards the core mantle boundary. And here down below, there are the large low velocity provinces that you will probably be familiar with. And the question really is, what is the origin of that heterogeneity, these drastic reductions in shear wave velocity, but to some extent probably also in P wave velocity. And what one can see in the data, in the seismic data, if one looks, one can see that on average, so the standard deviation of travel time variations measured here by Bolton and Masters at 25 seconds dominant period, plotted here as a function of the ray turning depth, so how deep the wave has traveled into the mantle. We see that starting from the mid-mantle on towards the core mantle boundary, we get this prominent increase of the standard deviation of this travel time residual signal. And this is pointing to something happening towards the core mantle boundary. Interestingly, for the measurements for the P waves, we don't see any increase of the standard deviation as a function of ray turning depth. And so this difference here is what people have often taken as an indication that there might be variations in chemical composition that are causing the signal, or other effects. You might think of not only chemical variations, but also the post-perovskite phase transition. And down at the very base of the mantle, there might be effects of melt or other interactions from the core with the mantle, for example, an iron enrichment or such. And we will look into this later on with synthetic data. So the origin of the heterogeneity, as I said, could be a chemically distinct material above the CMB, but we also have to take the fact into account that we have large lateral temperature variations that we expect in the deep mantle, especially in the hot upwelling plumes. First of all, we expect a high CMB temperature, and current estimates of the temperature at the core mantle boundary are on the order of 4,000 Kelvin, perhaps a little less, 3,800, but definitely not close to 3,000 or 3,200. From that, we expect a very strong temperature drop going from the core into the mantle. So we have a large thermal gradient across D double prime that is likely on the order of about 1,000 Kelvin or even larger. And that will lead to a high CMB heat flux that could be around 10 terawatts, or even some estimates go up to 15 terawatts, which is on the range of about 30% of the total mantle heat budget. That means what leaves the mantle into the crust. This is quite some substantial amount. And especially from this estimate here of the temperature gradient in D double prime, we would expect that plume access temperatures down at the base of the mantle are on the same order of magnitude of about 1000 Kelvin. And there are reasons why the plume access temperature then decreases while the plume goes up towards the surface due to effects of adiabaticity in the mantle, some effects of subadiabaticity due to internal heating. And so plume access temperatures at the base of the lithosphere and the asthenosphere are estimated from petrology to be on the order of about 250, 300 Kelvin. But this can be brought together with these large plume access temperatures at the base of the mantle. Okay, so if we have this idea about a quite high CMB temperature, we can run mantle simulation models, and here I show one model in 4 different views. We see the temperature anomalies here, red hot and upwelling, and the blue is the cold downwelling, as you can see here nicely in the upper right view. This is a model where we have used a plate motion history lasting for 200 million years back to the present. We solve in these models for the conservation of mass, momentum, and energy. And this is a treatment of the equations in terms of a Stokes flow of a compressible fluid. So we always run models taking compressibility effects into account, because especially we want to get these temperature effects in the plumes correctly and their depth dependence correctly. And for that, you need to take compressibility into account. So these models are parallelized, typically on about 512 to 2488 processors. And this is a multi-grid finite element solver. This is the code Terra that has produced this simulation that you see here. And currently we are working in our group heavily towards a new mantle circulation software, which is termed Terra Neo. And we hope to have the updated models from that software ready by roughly end of this year. So simulations that we currently do with Terra still are having about 670 million grid points. So it's close to 10 to the 9. And this is important to be able to run these models at Earth-like convective vigor. That means we can choose the viscosity such that we get roughly the correct RMS velocities in the asthenosphere to drive plate tectonics with what we observe on Earth, about 5 centimeters per year. So this is to a large part controlled by the viscosity that we impose in the models. Okay, so now we have such a model, but we want to know, is it Earth-like or is it just some model planet? So how do we go about that? We try to always do a quantitative assessment of our, what I call here, geodynamic hypothesis. This means any of the input parameters that we choose for the mantle circulation models is a set of or one hypothesis, and we need to test it. And part of the hypothesis could, for example, be the high CMB temperature compared to a lower one. So we run these computational fluid dynamic simulations. We create 3D mantle circulation models, as you've seen before, and that gives us a prediction of the present day 3D mantle structure. And in addition to that, a time evolution. I will not look into this today. I will focus on the present day mantle structure. So we have a synthetic Earth model or some model planet that we can investigate, and we need to assess it against Earth observations. And the Earth observations of interest are mainly seismic data, which I do in my group. And then also we can check about other data sets like the GeoEat, rate of true polar wander. We can also go backwards in time. That's what the group of Peter Bunge does here in Munich. And you can then check the evolution of the surface in terms of vertical motion against the geologic record. And you can look into the geologic record whether you see signals of subsidence and uplift. But here we want to focus on the seismic part. So that's what I mentioned before. All of my work is around that theme of trying to build a quantitative link from temperatures to seismic data. So this means that from the signal and temperature normally in terms of the magnitude on average, we want to go through seismic heterogeneity all the way to the seismic data in terms of the travel time variations and the average signal in that, as we have seen before from the Bolton and Masters data set. So the first step is we need to go from temperature variations to seismic heterogeneity. For that, we use thermodynamic mineralogical models. Here we use the model of Thomas Kust, whom I mentioned before, and that is similar to Hephaestus from Lars Stick's route. So the code that Thomas wrote during his PhD work is called MMA-EOS, and that produces mineralogical tables just as Hephaestus does, or Perplex. So we get here shear wave velocity, P wave velocity, and density. I only show the shear wave velocity table here. So you see all the values as a function of depth or pressure, and here temperature on the x-axis for the anharmonic part. So without the anelasticity correction, you get this by computing equilibrium phase assemblages through Gibbs energy minimization. And once the code has obtained the stable mineral phase assemblage, one can get at the elastic moduli and density through equation of state extrapolations or interpolations for pressure and temperature. Important is that this actually captures the nonlinear temperature dependence of the anharmonic part of the mineralogical mapping here. I want to later highlight this a little bit, but now let's see how this will look like if we map the temperatures to seismic velocities. You see here that's the same color scale, but if you look closer in the upper mantle, you see effects of the phase transitions at 410 and 660, and in between where we get much more short scale heterogeneity compared to the temperature field here. I will highlight this once more later in a blow up, but now the idea is really from the heterogeneity in the model, not to compare it directly to tomography in this case, but really to predict a surface observable, so the seismic data at the surface, some waveforms, and to extract from the waveforms the signal of travel time residuals, so that we can compare later on to this data set of Bolton and Masters that I show here again. And to do that, we need to run 3D wave propagation simulations. And I will also point out later in more detail why it's important really to use full 3D wave propagation and like using SpecFEM 3D globe, and not to do ray tracing or other things. I will at the very end in the outlook also show that this might have some applications, but for this quantitative link that I want to do here, we need to do 3D wave propagation. In doing that, we face these different nonlinearities and some challenges. And first of all, in the anharmonic part, we have a slight nonlinearity of the elastic parameters and the densities from single mineral phases. But this is not strongly nonlinear, but strong effects come into play once we have changes in the phase assemblage of the minerals. That means close to phase transitions, we will have very strong effects. Then we have a nonlinearity due to mineral anelasticity, because we have a strong temperature dependence of the quality factor Q that is important here. Actually, it's often treated with exponential dependence here on temperature. And in addition to that, we need to combine what the mineral anelasticity in itself does with a skewed temperature distribution from the mantle circulation model. This will also be shown later in a figure, how skewed the temperature field is. It's not symmetric around the mean temperature in the mantle circulation model with compressibility. And at the end, also a third nonlinearity we need to take into account is our 3D wave field effects, especially in complex media like the mantle circulation models, which have structures on much shorter length scales compared to tomographic models. Current tomographic models have length scales of 200, 300 kilometers and more. And in the mantle circulation models, we have slabs in the upper mantle that are about 100 kilometers thick. So for the nonlinearity on the anharmonic part, we see here that the phase diagram that I show here from Hirose 2002 strongly depends on temperature. This is at 1600 degrees C, and here we have 2000 degrees C. And I don't want to go in all the details of these mineral phases, but you can see the phase boundaries here. They change quite substantially for these temperatures, and this actually leads to a certain fact that the temperature sensitivity of the seismic velocities here shown for the shear wave velocity, an image from the work of Schuberth and Visco Bertoloni from 2007, that at the phase transitions we get these spikes in the sensitivity here due to these dramatic changes of the phase assemblage. That means if you are close to the phase transition and you just slightly change the temperature, you might go into another stability field, and then the seismic velocities may be dramatically different. So these spikes here are all indicated for certain phase transitions, and this just outlines the effect in a conceptual way, why we would expect these strong peaks in the temperature sensitivity of the velocities close to the phase transitions. And that is what you can really see going from temperature to seismic velocities. Here I have a blow up in from our model. It's a big plume we have in one of our models. That's the temperature field here, the one I showed before, and mapping that to seismic velocities. You can see how, especially in the upper mantle, the shape of the plume here changes. If I go back in temperature, the plume actually gets thinner because we go from a higher viscosity material in the lower mantle to a lower viscosity. And so therefore you get this thinning of the plume, while in seismic velocities, you get this thickening of the plume at the 660 discontinuity due to the phase transition effects. And this is seen all around that depth range in the entire model. Also here, that's another view of a slab that's close to Kamchatka here. And that's temperature again. If we map that to seismic velocities, you can actually see that at the 660, there are some regions where you get actually lower seismic velocities, even though we know it's a high temperature, lower temperature because of the phase transitions. Oops, if I go back here once more. Sorry, that was one too fast. Here you have the cold temperatures in the slab, and the seismic velocity in a very small depth range might be actually slow velocity. And we can also look at that in a plot where we see the spectral power of heterogeneity in the mantle circulation model. That is temperature here. So we have for all depths in the model a representation in spherical harmonics degree up to 20. We see the effects of the low viscosity here in the upper mantle. We have reduced heterogeneity in temperature, but mapping that to shear wave velocity, we can see these bands of heterogeneity, strong heterogeneity to very high degrees, so very short scale structure. And we need to take this into account also when interpreting tomographic models. One has to keep in mind that one doesn't directly see the structure in terms of temperature because of the mineralogy that is involved, and that which is very complex in the upper mantle. Now I want to point out here the nonlinearity due to the mineral anelasticity. The effect here is such that what we get in the mineralogical tables for the anharmonic part are sound velocities measured at very high frequencies of gigahertz, megahertz to gigahertz frequencies because of the small sample size. So this is an illustration of a diamond anvil cell. Here is a small sample in there, and the actual sample size is on the order of maybe a few microns at most. Therefore, you need these very high frequencies, while for the Earth, we want to apply that at a very different frequency band in the range of millihertz to hertz. So many orders of magnitude difference here. And that means in the case of the lab experiments, we really measure in a kind of elastic regime, while anelasticity plays a role in the teleseismic frequency band, and therefore we need to account for this effect that anelasticity changes the seismic velocity with frequency, and for that we can apply a correction, and this correction for anelasticity depends on the attenuation Q, it depends on the frequency dependence of attenuation, and also on the activation energy of that attenuating process. And the three parameters here are not really well constrained, and later on I will explore the effects of this uncertainty in the modeling in more detail. But I want to especially point out here that this gives a very strong nonlinearity. We have here the shear wave velocity, and in the upper image, the P wave velocity, again, depth on the y-axis and temperature on the x-axis here. And what you see is the change in the mineralogical table due to the anelasticity for a certain set of parameters of the parameters I just mentioned. And the effect is more dramatic for the shear wave velocities. The color scale is such that these yellow reddish colors are below 1%, and then we go into the purple colors above 1% roughly. And we see that especially in the lower mantle for the positive temperature anomalies, we get, so here this white line is the mean temperature profile of a mantle circulation model, and everything above that mean temperature will get a strong change due to the mineral anelasticity, while the cold temperatures are hardly affected. So we are here in the very bottom range of the color scale. And now here you see the temperature distribution in one of the mantle circulation models that's work with Roddy Davis. And again, this is the same mean profile. And we see here the distribution of grid points with a higher or lower temperature for the different depth layers. And you can nicely see the asymmetry and the skewness of that. And you have to kind of convolve in your mind this skew temperature with the change due to the mineral anelasticity, and that gives rise to strong nonlinear effects, because this bottom part of the positive temperatures will be affected much more strongly than anything on the cold side here. Then quickly, some words about the wave field effects that we need to take into account, and why it's important to really do full 3D wave field simulations. This is an illustration of wavefront healing, a work from a PhD student of Heiner Hiegel here in Munich many years ago. And this you probably will have seen. This is a low velocity body. We have a plane wave that travels down to the right. We see different time snapshots. So here in this time, we have the wave within the low velocity body. The wave here is delayed, and this delay here then actually over time is healed away, because energy from the sides can travel into the middle region here, and later on you will get no signal, and that can be equivalently represented with these banana donut kernels that you will be aware of. Now, important to note here is that this wave field will travel through a mantle where we have the length scales and magnitudes of the seismic heterogeneity, which are controlled by the dynamics of the convecting system. So the energy input due to internal heating, and also due to heat flow from the CMB, and the viscosity will mainly control what length scales and magnitudes of temperature anomalies, and with that seismic heterogeneity one will get. And this can be explored through running wave field simulations in mantle circulation models. Wave field effects in complex structures depend on a number of factors. Wavefront healing here, for example, depends on the size and the wavelength of the heterogeneity. It depends on the location where this anomaly sits between source and receiver. So here below we see two different banana donut kernels, finite frequency kernels, here for a period of 10 seconds and here for a period of 34 seconds. S-wave kernels, that's the work of Christophe Zaroli. And the same size anomaly will be seen differently by these two waves, and also a larger anomaly might lead then to different signals. But it's also important to understand that the same size anomaly will have a different effect, whether it's close or when it's close to the source or close to the receiver, compared to the first scenario when it was sitting in the middle. And in the true Earth, we will have a combination of many of these anomalies seen by a wave traveling here in this simplified fashion, represented by the banana donut kernel. And this needs to be really explored in a full wave propagation simulation scenario, and cannot easily be predicted with either ray tracing or finite frequency kernel predictions. So for the wave propagation simulations, I mentioned before, we use Spectrum 3D Globe. That's also why I'm very happy about CIG hosting and caring about that software. The Spectrum 3D Globe software uses the cubed sphere mesh. So the cube is blown such that it then reaches the sphere. We have the subdivision into 6 chunks on the surface, and here you see a view inside the mesh. Many of you will probably have seen this before. In the center of the Earth, in order to avoid singularities, the cube is still retained, and then stretched such that in a certain depth range you reach the full sphere, and then the mesh is spherical all the way to the surface, with some grid refinements with depth, as you can see here in the upper mantle in particular. So this is a spectral element method, has the benefit of high accuracy and the spectral convergence behavior. Just a few notes for people who are not so familiar with the software. It is based on the weak formulation of the wave equation, and implicitly incorporates free boundary condition. So we don't have to care about the free surface. It's taken into account implicitly here with that formulation. The method leads finally to a diagonal mass matrix, and that's nice and important because it leads to a very efficient parallelization. And then finally we get really realistic wave fields from the simulation. We can take effects of topography into account if we like, effects of 3D crust and mantle, also 3D anelasticity variations, full anisotropy, if needed, effects of self-gravitation and ocean loading, and this in the end can really be very realistic. So how do we now go from temperature variations to the seismic data? We have phase 1 problem, and that was something I think that would be interesting for people to know, that we have to project temperatures from the grid of the mantle circulation model to the Spectrum 3D grid. So I want to spend a few minutes on discussing that technically. How do we do that? So the grid in the Terra simulations is based on an icosahedron, and we cannot directly go to the 3D wave propagation simulations. We need to make a few loops. So what do we do? The icosahedral mesh is the icosahedron also mapped onto the sphere. Here you see the icosahedron inside, and often it's treated either as 10 diamonds or 20 triangles, large triangles. So from here, this is the North Pole, for example, and those 2 points here, they span one of these triangles. And then this icosahedron finally is blown to the sphere. We take curvature into account, which is not shown in this illustration. And the grid at the surface is successively refined by midpoint subdivision, which is shown here in the bottom right. We start with this macro triangle, and then go to finer and finer levels of the subdivision, so that we finally reach an almost equidistant grid with roughly 10 kilometers grid spacing. That's the current resolution that we use. And with Terra Neo, the new software that I mentioned, we want to head towards roughly 1 kilometer grid spacing in the long run, with exascale computing power that is up on the horizon. The surface grid then is radially extended down to the CMB, as you can see here. So the points in the different radial layers are at the same latitude and longitude location, which is nice. We can explore this later on. So this is a quite regular mesh in some sense. And each processor in Terra gets a chunk of each of the diamonds. So this is shown here with the colors. So the first processor, for example, gets all the 5 parts here and 5 of the diamonds on the northern hemisphere. If we, for example, take this yellow one, then it gets the same portion, always a few triangles away, but in the same location on the next diamond, so that we explore some effects from speed up in the computations. And each of the processors gets the entire depth column below that triangle here. And that makes it a little bit more tricky in how we get this into other grids, but I show you how at least I do this in our codes. So now, how do we get the temperatures? We read temperatures just relevant for the local chunk in SpecFem. So here, this chunk means we have one processor in SpecFem, and in order to reduce the memory we have to load for that chunk, we just need the local temperatures around that. In order to do that, we read the 2D surface grid XYZ Cartesian coordinates on the main processor, and we create a search tree for that surface grid. Then we create masks for all the points inside a region around each of the chunks barycenter. I have an illustration for that. So this is the SpecFem domain decomposition in for a certain case, and so all the colors show portions of the grid that a specific processor would be assigned to. So we compute the barycenter of that red chunk here, for example, and then in a certain kind of circular region around that barycenter, we search for all the points in the mantle circulation grid that fall into that circle and make a mask, so that the main processor then later can send only the temperatures for those grid points to that specific chunk here. So we read the temperatures on the main processor layer by layer, also throwing away all the layers that we don't need anymore to reduce the memory on the processor. And then for each of the layers, we send the local temperatures specifically to each of the processor according to the mask that we created before. And then one important point is that we project the temperature field of the mantle circulation model to SpecFem and not the seismic velocities. That is specifically done because of this effect of the short scale variations in seismic velocities due to a smooth temperature field. So this high sensitivity of the seismic velocities due to temperature that I showed from the Sticks root work, because we would actually have more difficulty in later interpolating these short scale variations in seismic velocities. It's much easier to actually interpolate for the more smoothly varying temperatures. So we project temperature here to the SpecFem grid. What we do is we find the 3 nearest neighbors for each Gauss-Legendre-Lobato point in SpecFem within the 2D surface grid. And that's done with a KD tree search, which is actually quite efficient. It's running quite fast. And we can subdivide the lateral search from the radial search. So we then do a second search in radial direction, getting the layer above and below the current point in SpecFem. And that's really very fast because it's just around, 256 layers, for example, which we need to search for. And then we do an interpolation within the nearest neighbor triangle, first in lateral direction and then in radial direction to get to the temperature at the local point. So how do we do that interpolation? the interpolation is done laterally with barycentric coordinates shown here. So that is the current point in SpecFM, and within that triangle, so these points V1, 2, and 3 would be the grid points from the mantle circulation models. And the barycentric coordinates work such that you can get to that point V here by this linear operation that lambda 1, 2, 3 are the barycentric coordinates. You multiply that with each of the according vectors, and the same can then be applied also to the temperatures to interpolate here to that point in the triangle. The sum of all these barycentric coordinates is 1 is unity, and if the point V here is within that triangle, so really within, not on the edge of the triangle, then all of the lambdas are all positive. And with that, you can check that your nearest neighbor search also went fine. Okay, here we have a simple 1D linear interpolation in radial direction, as you can see. So upper layer triangle, lower layer triangle, and then just this is the local SpecFM point we interpolate to that. A few more technical words, and then I think I'm done with that. We convert the temperatures to SpecFM, as I said, and from there we then converted the temperature in SpecFM to seismic velocities and to density. You just need to search the mineralogical table to get the anharmonic velocities. You can apply an anelastic correction if you want, and vary the parameters in a systematic fashion. And in order to do comparisons to seismic observations, we often work with travel time residuals, so perturbations around a mean arrival time. And for that, we need to compute the arrival time or waveforms also for cross-correlation measurements. We need to simulate waveforms in the 1D average structure of the MCM. And there we also do a specific procedure. We read temperatures layer by layer again on the main processor, and then we interpolate all the layers in depth according to the mineralogical table, because the mineralogical table is much more finely spaced in depth compared to the mantle circulation grid. And then we have a high number of fine layers. In my case, currently it's about 1,400. And for each of the fine layers, we convert the temperatures to seismic velocity. So these are still 3D velocities. And then we compute the averages in each of the fine layers for VS, VP, and rho. Because in this case, for the 1D profile, you also get the fine jumps at the phase transitions. So it's not a wise thing to just take a temperature 1D profile and map that to a 1D seismic velocity profile, because you will not get the effects correctly of the phase transitions. So this is the strategy that we use. Okay, a few words for the wave propagation setup with SpecFM. We in 2012 and 15 computed wave fields down to 10 seconds shortest period. That is for this parameter nex in SpecFM of 480. It amounts to about 4 times 10 to the 9 degrees of freedom, is about 200 gigabytes of RAM. And we have used about something between 500 and 900 cores on our supercomputer here in Munich. And for 1 hour of seismogram, this typically needs about 2 to 3 hours of wall clock time. And so you get a modest compute budget, let's say, for 20 to 30 earthquakes, which is a minimum for 1 model test, but you want to test a lot of mantle circulation models. So this can finally also get quite large. Just to compare this with the Terra simulations, the mantle circulation models, there we use somewhere between 10 to the 8 and 10 to the 9 grid points. So this is the current resolution. Also is about 200 gigabytes of RAM. As I said, between 512 and 2048 cores. And these simulations take much longer, on the order of about 100 hours wall clock time, sometimes longer, depending on how long the plate motion history is that you impose as surface boundary condition. But this is not kind of the end in SpecFEM. The goal would be to go to wave fields with shortest periods of below 5 seconds. This goes to more than 10 to the 10 degrees of freedom, next 960 in SpecFEM. The RAM would go to a few terabytes here. As you see, you need much more cores, but this nowadays with exascale computers should not be a problem and can go even higher than that. The wall clock time will still be on the order of hours, let's say. And if you want to then increase the number of earthquakes for one model test, you have to go somewhere to 2 to 6 million CPU hours. And if you want to test more models, then this can get a bit more heavy. And as you will probably know, teleseismic waves, we would probably like to go to 1 second, but due to this very almost exponential increase in compute time, for decreasing periods, we probably will be quite far from that still, at least in a routine application sense. Okay, so finally we know how to go from the Mantle circulation grid to SpecFEM, to the cubed sphere grid, and now we can run wave propagation simulations in that. And here I have one illustration where you see the 3D wave field in the synthetic 3D structure. So the wave field here in pink and greenish colors. The shear wave velocity heterogeneity in this case is colored in this brownish red and blue fashion. And what is important to note is that you now get synthetic wave fields and synthetic seismograms at the surface of the Earth fully independently of any seismic observation. So this is something which is important so that any check against the seismic observation is not leading to some circular reasoning. So imagine you take a tomographic model which is built on seismic data, you run wave propagation simulations for that, and you compare to the seismic data again. That is not as helpful as really starting from the synthetic theoretical prediction what the Earth could look like. And so we can then get seismograms at any location on the Earth that we like, and typically as we put many more virtual seismometers on the globe as are there on the real Earth, we can, for just 20 earthquakes, get here in this case about 3 million P and S wave travel time measurements. So a data set that is comparable in size to the real data sets, although we have a lower number of earthquakes that we simulate. So here we now test the simple model planet that we have. I don't want to go in all the details. I just checked the time is already quite long. We just look at the Mantle heterogeneity. We checked different frequency bands here to look at dispersion effects that I mentioned. And we have this really large number of virtual stations to get a global homogeneous illumination. Here is one example of a seismogram so that you just see how realistic that can look for a Mantle circulation model without crust still. This is, here I pointed out different phases just to show you that this really gets close to what we would see in the real Earth, except that due to uncertainties in the mineralogy and the mean temperature of the Mantle circulation models, the absolute times may be a little different. So a one-to-one comparison with real seismograms is still a little tricky. And therefore, we often look at statistics. Here I plot the travel time residual measurements for a single earthquake. This is an earthquake in Iceland. And at each of these pixels, we have a seismometer and we plot the travel time residual measured at that specific spot here in this map. And you can only get that because of the many virtual stations. For a single earthquake, you cannot plot this for real data because you have just a few hundred stations maybe, but not here in this case, about 15,000 on that part of the globe. So we look at epicentral distances between 30 and 90 degrees for P and S waves. And you see here P waves have about -5 to 5 variation in seconds in the color scale, and almost twice for S waves, -10 to 10 in this case. This is an example of the dispersion that we get for the different frequency bands here. So from 15, 22, 34, and 51 seconds. And you see the change in the travel time residual with frequency in a purely elastic model. So this is not an effect of attenuation for P and S again. So here we also can look at the variation in these maps of the travel time residuals. These effects here that you see are related to the nodal plane of the radiation pattern. I don't have time to really go into the details, but this is something interesting to explore. What I want to focus on here now is these travel time dispersion effects. So from wavefront healing, if you plot long period minus short period signals plotted against the short period signal from wavefront healing, you would expect kind of this curve here with a negative slope. And if we look at real data, again, work from Christoph Saroli from Strasbourg University, you see here that at least for the slow arrivals, we get a similar behavior, that we have this decreasing slope here of the median of these measurements. It's not as obvious on the fast side, so the earlier arrivals. Now we can look at that in our simulations. This is for a single event, one earthquake only. And we see here in the mantle circulation models, we get this effect that probably some wavefront healing happens, but it's much more complex than just this linear simple case. Again, as I mentioned, there are a lot of nonlinear effects. It also depends on the structure. It looks different for the earthquakes in fast regions, for example. Then this entire signal is shifted to the negative side here. But in general, this is a signal that we can use to understand length scales of the structure and the magnitudes, because this will change, the dispersion effect will change by changing the mantle circulation model. And we can, with that, hopefully turn it around at some point and say, okay, what are the length scales and the magnitudes of heterogeneity in the real Earth, by better understanding the signal for different mantle circulation models, so that we get a handle on that. So maybe I can briefly go here. So this is for all earthquakes, 20 earthquakes that we simulated in this case together. The signal gets a little weaker, but still you can see here this decrease of the median and means in black and red. For the P and S measurements, it's a bit more complex here in the P waves. So this highlights again this nonlinearity effect that I mentioned. But the signal that we get on average for this dispersion between 51 seconds and 15 seconds period is 0.6 seconds for P waves and 1 second, sorry, for S waves. And this is fully compatible with the observations also, for example, from Karen Siegloch and Christoph Saroli, if you because Karen Siegloch worked mainly on P waves, and Kasra Hosseini and Christoph Saroli worked mainly on S waves, but they find similar signals in the dispersion on average. So my first conclusions, we have a first quantification of wave field effects in 3D structures for dynamically consistent length scales and magnitudes of seismic heterogeneity. So from the mantle circulation models, we know that the structures are dynamically consistent. We get a clear travel time dispersion signal in elastic models. That means we only get diffraction, focusing effects and such. And the signal here is 0.6 seconds for P and 1 second for S, as I mentioned, is fully compatible with observations, and around half of that signal actually comes from lower mantle. I don't have time for the details, but this is work from 2015. And here again, as I mentioned, the compatibility with the seismic observations. Now towards the end, I want to actually come back to this data set of Bolton and Masters and the magnitude of the travel time residual as a function of ray turning depth, the behavior of P and S waves that had been different. So the band of the signal here is due to uncertainties and different quality of data, so different categories that they used for the data according to certain criteria. And So this is the possible range of values for the mantle signal only. So the crustal effect was taken out in this case. And now the simulations that we did in a purely thermal model, so no chemical variations in the model, are shown here. For the P waves, we find that the signal stays more or less constant with ray turning depth, while we get this increase towards especially the core mantle boundary in the S waves. And that is quite interesting that we get this different behavior from P and S also in the purely thermal model. And now the question is, what about uncertainties? By how much would these curves change if we take effects of anelasticity, for example, into account? We haven't done this in this first work here in 2012. What are effects of the crust and lithosphere, which we excluded for the moment, and also effects of seismic data noise could be relevant. What I want to show you here towards the end is the effects of anelasticity. So here we explored this by changing the parameters of the anelasticity correction in a systematic fashion. The elastic part here is shown for these dashed dotted lines. And then we have a maximum unelastic correction, so the maximum plausible values for the parameters that we can choose. And this is shown here. We again see P waves stay more or less constant with ray turning depth, and we have this increase of the signal for the S wave travel time residuals. And depending on the parameters you choose, you get within this band of the observations. And we definitely don't go too far out here with the anelasticity. And we also did a simulation where we, in addition to the anelastic correction, also included attenuation in the simulations with SpecFEM, and you see that the change does not make much here. This signal from attenuation doesn't dramatically change this behavior. Okay, so a second set of conclusions. The statistics of long period P and S wave travel time residuals can be reconciled with a purely thermal origin of seismic heterogeneity, at least in the way here I presented that in statistical terms. We have a systematic investigation of the mineralogical uncertainties in terms of the anelasticity correction. That was the work from 2021. And we get the full nonlinear relation between temperatures and seismic travel time residuals. So nonlinearity in the anharmonic part, the nonlinearity due to the anelasticity in combination with the skewed temperature distribution in the mantle circulation models, and the nonlinearity due to the wave propagation effects. And this really means we have a physically consistent link of temperature anomalies to the seismic travel time residuals. And this can, I think, be further explored in future. Still, from the mineral physics community, it would be nice to have better constraints on the parameters that govern the mineral anelasticity. Then one could narrow down that range of values I just showed before. And in summary, we started off with generating high resolution buoyancy distributions in the mantle by modeling mantle flow at realistic Rayleigh numbers. Our mantle circulation models recreate, with this work that I presented here, a quantitative link between the geodynamic Earth models and seismic observations at the surface. So not stopping at a comparison to tomography, but really go all the way to the surface observations. And some ongoing research and outlook. I currently work towards creating synthetic seismic data for mantle circulation models such that we span the entire teleseismic frequency range. What I mean by that is we compute, in addition to wave fields with SpecFEM, some normal mode spectra, long period normal mode spectra with a code from David Al-Atta from Cambridge University. And we also predict splitting functions together with Paula Köhlemeyer from Oxford. This is currently also work where we try to look at the effects of uncertainties in the lower mantle structure, related also to plate motion history models and the absolute reference frame behind that. Then, in addition to the long periods, the low frequencies, we look at high frequency travel time residuals by computing ray tracing, so an approximation of the wave physics. But it's interesting to see differences between 1D and 3D ray tracing. For the 3D ray tracing, we take a code from Nathan Simmons, from Lawrence Livermore, and that probably is a bit more realistic than just a simple 1D ray tracing. And for some applications, the 3D ray tracing, I think, can be used to do a quick check on some of the mantle circulation models. And also, again, with Christoph Saroli, we work on finite frequency kernel prediction, so banana donut kernels to compute travel time residuals in a quicker way with less computational cost compared to SpecFM, also for certain applications. This spans the entire range of frequencies, as I said, and then we can go into exploring effects of crust added onto the mantle circulation models and lithosphere effects and others. So this work can be extended, I think, quite a lot. And I mentioned this in the abstract to that seminar, that we go into some kind of virtual seismology in the mantle circulation models. We have a control on everything, and we can really learn a lot of the effects and understand better what nature provides us with in the seismic recordings that we measure.